Okay, let's continue. Last time we started chapter 5, the general structure of wave mechanics, which we review on this important quantum mechanical interpretation of those wave function and eigenfunction and expansion theorem and so on. So, and then we start to introduce this analogy between vector space in applied mass and also the very similar space which we call the Hilbert space in quantum mechanics. So there are a lot of common features between this vector space in mathematics and also the structures of wave functions and expansion theorem and so on in quantum mechanics. So this is the table of this comparison between these two. So most of the properties in the vector space that will have a corresponding properties in quantum mechanics. For example, this complete set of eigenfunctions that we mentioned many times, that's phi n, looks very much like a set of unit vectors in the vector space that we have this xyz unit vectors, the three-dimensional space. So the eigenfunctions plays the same role as the unit vectors in the vector space because they construct the spaces of all expansions of all these unit vectors. For example, this Fourier expansion theorem that we mentioned many times is precisely this application of such unit vectors and eigenbases. So any arbitrary wave function can be decomposed in terms of this complete set of eigenfunctions, and this looks pretty much the same way as we superimpose these unit vectors in vector space by arbitrary coefficient an, and we can construct any arbitrary vectors in vector space. Okay, so this arbitrary vector A plays a similar role as arbitrary wave function psi, which I emphasize millions of times, the difference between the arbitrary wave function and eigenfunction, right? And so this difference is precisely the difference between the arbitrary vectors that you can form by this linear combinations of a unit vector, which looks like plays the same role as the eigenspace, eigenfunction, eigenbasis. And likewise, in the vector analysis, you know that you add these two vectors together, you get another vector, right? So same thing happens in quantum mechanics, even though this psi1, psi2 are not vectors. Remember, the difference is that these wave functions in quantum mechanics are not vectors. They are functions, they are complex functions, right? But they follow linear algebra, very similar to this linear algebra that you find in the vector space. So when we add these two wave functions together, you get another wave function. So this is probably the more fundamental than this Fourier expansion, because when you linear superimpose all these different eigenfunctions, you formed a different wave function. Okay, so psi is the sum of these two, is also another wave function, but it's not eigenfunction. Okay, so it's any arbitrary wave function. So you can sum up all arbitrary wave functions, get another wave function. Okay, so like this summation of two vectors, get another vector. So you can consider this interference effect or this inner product between these two vectors in vector space, and you can also consider this so-called this overlap between these two wave functions. So this is definition of this inner product in quantum mechanics, which is the overlap integral that I introduced many times. So this plays the same role as this dot product between two vectors. So I guess by now you have a complete picture of what's we have now when we deal with this Schrödinger wave functions in quantum mechanics. Well, this psi follow pretty much the same rule that all those vectors follows in vector analysis, except this dimensionality is different. So In quantum mechanics, we are dealing with a complex, infinite dimensional vector space, which we call this Hilbert space. But in vector analysis, we only consider a real finite dimensional vectors in vector space. So later we will try to use a different notation invented by Dirac that you could represent such a sort of a vector-like object, which we call this matrix. For example, this any arbitrary wave function phi or psi inside this overlap integral, we could represent such a overlap integral by a product between a row matrix and a column matrix. So there is a matrix representation of these wave functions, which we will discuss in a moment. So let me just write it here. There is a matrix representation of those Schrödinger wave functions. For example, if you could actually write down this component of this phi star, which is the complex conjugation or Hermitian conjugate of this wave function phi of x. Okay, so of course this is a complex function, but imagine that we can actually represent such a wave function in this plot, and you could find this distribution of those wave function like this. And imagine that I could actually discretize all this x coordinates in such a way that it could actually go from minus infinity to plus infinity by as many discrete points as you like, say x1, x2, up to x infinity. So I can actually label the x coordinate by infinite number of discrete points. Okay? And I can actually store all this information of the wave function phi of x in that infinite number of, I should say, values, right? So I could actually call this phi of x infinity magnitude square, and this is phi xn square, and so on, and this is phi x1 square. Okay, so instead of using the continuous curve to represent such a Schrödinger wave functions or probability distribution, I could equally well describe same wave functions by a set of discrete points, okay, which I call this a row matrix. I can actually define this is a column or row matrix which stored all these discrete values of these wave functions at these discrete points. So this is phi x1 up to phi x infinity star. Okay, and this is so-called the matrix representation of the wave function, and you will see the meaning of the Hilbert space right away if you represent such a wave function in terms of the matrix. So, and this is a row matrix made of this discrete values of these wave functions at those discrete points in X space, and how many elements are there? How many matrix elements are there? Of course, infinity, because I can mesh this x-axis as many points I like. The more points I mesh, the more accurate description I achieve, right? Okay, so I could mesh as many points as possible, and the maximum value number of the mesh points is of course infinity. So, and this is an example of a vector living in an infinite dimensional space. Some kind of a vector. You know that the vector could be also represented as a matrix, right? So if you like, you could actually write down this x unit vector as what? 0, 0, 1, right? This is the coordinate of the x unit vector. And 0, 0, 1, of course, is written in terms of this column or row matrix form. Okay, so I can also call this row or column matrix unit vector x. Okay, so a vector living in a finite dimensional space is nothing but a finite dimensional row or column matrix. So the difference between the vector space and the Hilbert space is the number of dimensionality that you could represent such a vector. So in quantum mechanics or Hilbert space, we use infinite number of dimensional vector in the matrix form to represent any arbitrary Schrodinger wave functions. So, and likewise, you could actually represent this column matrix, say psi of x is a column matrix which stores all these matrix elements, which is nothing but the values of wave function at particular x coordinates, psi x infinity. Again, psi of x could be defined as the infinite dimensional vector in the form of the column matrix. And in this matrix form, it is very easy to understand this inner product and overlap integral. This is precisely the dot product in the vector space, because you could easily represent such a integration of overlap integral in terms of a complete, this discretized summation over all this xn, n from say 0, 1 to infinity of this phi star xn psi of xn, right? So instead of using the continuous integration, I simply just sum over discretized version of this integral. Sum over all this product between phi star and psi at all these points, xi or xn, and I sum over all such products. And this is equal to precisely this integral. But what is this? What is the product of all this phi star xn and psi of xn? Well, this is precisely the product between these two matrices. This is the product between a row matrix and a column matrix, right? So the row matrix has this matrix elements phi star x1 up to phi star xn, and column matrix is made of this matrix element psi x1 up to psi of xn. So if you simply perform such a matrix product between the row matrix and column matrix, which you in high school mathematics you have learned this. Okay, so the product between the row matrix and column matrix is again the number, right? And what is this number? Well, this number is precisely the sum over all this discretized product, isn't that? If you remember your high school mathematics, and this matrix product is what? This is phi star x1 times psi of x1 plus phi star x2 times psi x2 and all the way to the final matrix element. By making such a different representation, you know immediately the connection between the vector analysis and the Hilbert space. Okay, the Hilbert space is nothing but the vector which made of a complex values and living in an infinite dimensional space. And this is called the Hilbert space. And we will represent Schrödinger wave function, but also the other operator, all the quantum mechanical operators could be represented in the matrix form. And all this computation involves the matrix product. So it's always matrix, matrix, and matrix. So by now, you should gradually switch your language from wave function, the Schrödinger-like wave function, to the matrix representation of the wave function. Okay? And this is the essence of quantum mechanics, which allows us to use this vector space-like analysis to rewrite this Schrödinger equations and quantum states in terms of a matrix. And Dirac invented such a great symbols, Dirac operator, also in the form of the matrix, and which greatly simplified all quantum mechanical calculation. And this is what we should learn. Okay? This is real quantum mechanics, rather than just solving for the one-dimensional potential problem. And from now on, we should apply such an analogy for all the discussion below. Okay, so again, this operator in quantum mechanics can also be defined in the form of a matrix, which looks like precisely the matrix that you are familiar with in vector analysis. And we could define the operator in the matrix form, Mij, and we could also define so-called Hermitian conjugate of that matrix, which is Mji star. And we call this Hermitian conjugate of this operator a dagger. So if the A operator is defined in matrix form with a matrix element Mij, what are those Mij will be discussed later. And a dagger operator is defined by this Hermitian conjugate operation, which you switch the matrix element between, say, from this Mij to Mji, and you put the star. When you put the star, you actually collect only this complex conjugate of this complex matrix element. So for example, if this value of Mij is actually A plus IB, if I put a star, there is A minus IB. So this operator in quantum mechanics follow this matrix in vector space. Okay, so this operator actually transform from one to another, follow the same rule that we know for this matrix transformation. And this operator in quantum mechanics actually transform one vector to another. Okay, so which is precisely what it means by this operator. Okay, so the operator really operates the states, and when we perform such a quantum mechanical operation, we transform one vector to another vector. Okay, so this vector, I use a quotation mark, which represents this quantum state. So let me just use this mathematical formula for such a kind of a interpretation. For example, if phi and psi are two quantum states, as I mentioned, any quantum states or wave functions could be represented by a row of the column matrix, right? Suppose this phi and psi are some arbitrary column matrix. If I apply this operator A onto this state phi, and I in general get another quantum state, right? So this is quantum state 1, and on the left hand side, if I operate this phi state phi by an operator A, which is also the matrix, and I get another quantum state, which I call this quantum state 2. So this operation follows precisely the rules that you know very well from your high school mathematics, namely the matrix product. So if the matrix A represents some kind of a quantum mechanical operation, which is made of a n by n matrix, and this column matrix, you know that in the n-dimensional space where n goes to infinity, so it is an n by 1 matrix, right? So the resulting states is also column matrix, which is also n by 1 matrix, right? So you know from your high school that if you multiply a matrix with n by n by n by 1, and you get n by 1. Yes or no? Okay, so the multiplication between the n by n matrix and n by 1 matrix is the matrix of n by 1, right? So another important review is that, so if I multiply 1 by n matrix by n by 1 matrix, what do I get? It's a 1 by 1. So the 1 by 1 matrix is just a number. On the other hand, if I multiply a matrix of n by 1 and 1 by n, what do I get? I get a matrix, not a number. I get n by n matrix, right? Okay? So, and we will take advantage of such a matrix product and multiplication that you're already familiar with in your high school, and apply it here in quantum mechanics when we deal with this operation and transformation of the quantum states. So now you have a very clear picture and analogy between quantum mechanical operation and the matrix product in vector space, right? So when we say that we perform a measurement, what we really mean is this. Okay, so we apply a matrix which represents the quantum mechanical operator onto some quantum state, and we take the measurement, okay? And then we see what it reports, what it returns. Okay, so it returns to us, there's another quantum state, which I call this psi, which is again n by 1 column matrix. Okay, so there's a complete analogy between the vector space, vector analysis, and this matrix representation of a quantum mechanics. So from now on, you should always consider the quantum mechanics in terms of the matrix mechanics. Okay, quantum states is column row matrix, and operators are n by n matrix, and they satisfy the linear algebra, so-called linear operator. So let's take a short break. When we come back, let me just finish all these linear properties of this operator and quantum states in terms of matrices. This is a very important introduction and foundation of all the remaining chapters of the course. 有什么地方不明白的吗？请举手发问哈。这边是一个蛮重要的一个关键，就是我们在数学上能够重新去 reformulate 这个 Schrödinger wave function 哈，以及它的一些数学的一些运作哈。那这些数学的运作其实是跟我们熟知的这些矩阵，还有向量空间啊、向量分析、矩阵，这些是息息相关的哈。那所以请各位同学就是把课本里面相关的部分好好的了解一下啊。那未来我们就比较少用 Schrödinger wave function 这个函数来描述这些 quantum state 那取而代之呢，就是用这些向量跟矩阵，尤其是矩阵。好，因此呢，这个矩阵跟向量以及量子状态 （quantum state） 这个关联，各位一定要务必要理解。OK， 这才是进入到量子力学哈。前面都是量子物理跟近代物理的部分哈。真正的力学的部分，其实就是 matrix 的这些计算哈，以及我们会提到的狄拉克符号哈 （Dirac notation）。Great. I suppose everyone is smart enough and really understands this analogy. Great. So let's discuss this linear properties of the linear operator. As I mentioned, this size or wave functions are row or column matrices, and they are nothing but a vector in the infinite dimensional space, and they follow precisely the same properties as vectors in linear algebra. So, for example, this operator A acting on this states alpha 1 psi 1 plus alpha 2 psi 2, which follow the same rules that you expect between a matrix and n by n matrix and n by 1 matrix. This is alpha 2 A psi 2. Okay, so and this alpha 1 psi 1 plus alpha 2 psi 2 is just a linear superposition of two wave functions with the arbitrary coefficient alpha 1 and alpha 2. When I make such a linear combination, this is again another quantum state as I mentioned, right? So, but alpha 1 and alpha 2 are just numbers. So you consider this as just a matrix of n by n times alpha 1 coefficient times n by 1 matrix plus alpha 2 times another n by 1 matrix. If you simply just translate everything in terms of matrix, and you know this property is just come naturally, because this alpha 1 is simply just a coefficient, you can simply just pull it outside of this matrix product, because this is just alpha 1 A acting on this psi 1 plus alpha 2 times this n by n matrix multiply by psi 2, right? And so then you could consider this, as I mentioned, this psi 1, psi 2 are just this matrix representation of vector. And then you apply the matrix onto that vector, you get another equivalent operation, which you can simply just pull this coefficients in front and follow this linear algebra of the vector in vector space. Okay? So let's just look at this definition of the Hermitian conjugate operator. As I mentioned, the Hermitian operator, a Hermitian conjugate operator is the, this is Hermitian conjugate. A dagger is the dagger of A. Okay, so again, think of this as a matrix. So this is n by n matrix, which represent any quantum mechanical operator. So if you put a dagger on top, which means that you simply just take the Hermitian conjugate of that matrix, which is what? This is AJI star. Remember that. Okay, but this is just a matrix kind of analogy, but we will define formally based on this overlap integral. Okay, so this in quantum mechanics defined by this identity. Okay, so let me explain. So quantum mechanically, we should define Q dagger or dagger of Q in this way, right? So this Q or Q dagger is an operator in quantum mechanics which will operate onto this quantum states or wave function on this right? But what is this? Well, this means that you could simply just combine these two, the two operators on the left, right? So from the right, this psi star and Q dagger. I don't know what this Q dagger is, but this is the way that I define my Q dagger. Okay, so the Q dagger appearing in the middle of these two wave functions is defined as the Q operator acting on psi, and you take this Hermitian conjugate of this quantum states, and you make this overlap integral. So that's precisely what I mean by using this Q dagger. Okay? And this definition is really consistent with this matrix definition of the A dagger as a Hermitian conjugate matrix of the Aij. So because if I simply just use this matrix interpretation of this operation, so this is what? This is Q is actually n by n matrix, right? And psi is a column matrix made of n by 1. And altogether, this multiplication of these these matrices gives you what? Another different states with n by 1, right? Which I call this tilde. Okay, so now I need to actually take this Hermitian conjugate of these both objects, right? So what I do, following the definition of taking the Hermitian conjugate of a matrix, well, this is what? So let me just write it here. Q psi star. What is this? Well, this is Qij matrix multiplied by psi j, and you take the Hermitian conjugate of everything. And you know very well from your high school mathematics that if I make a matrix product like this, and I take this Hermitian conjugate or complex conjugate of this matrix, what it means is that I should interchange, right? I should interchange between these two matrices, and I should actually add this complex conjugate on all these two matrices. So this is by definition psi multiplied by Q, but I should put it star, which is psi j star multiplied by Q j I star. Right? So that's from this matrix product. And if you simply just use the matrix product rules to rewrite this definition of Q star, and what I get is this one. This is the x. What is this? This is psi star and Q j I star and psi of j, psi of I. And well, this is precisely the meaning of Q dagger, right? In the matrix form, this is nothing but Qji star. Okay, great. So which means that if I can rewrite this operator in terms of the n by n matrix, if I take the Hermitian conjugate of this A operator, equivalently, what I need to do is to switch the matrix element between Aij and Aji, and then I put complex conjugate on all these matrix elements. And this is definition of A dagger or Q dagger. But we should always remember that all this operation will be done in this overlap integral like this all the time. Okay? So the formal definition of the Q dagger in quantum mechanics follows by this kind of Hermitian operation. And right, so this is the definition of the Q dagger, okay, in terms of the overlap integral or expression value. Okay, so and later we will prove that if the operator is called so-called Hermitian and eigenvalues should always be real. So let me just define the Hermitian operator. A Hermitian operator is the operator where you can actually see this very easily, that in the matrix form, if A operator represented by the matrix A, and if A is the same as A dagger, then we call this Hermitian operator. Or if you take the expectation value of the A operator, which is the same as the expectation value of the A dagger operator, then this A operator is Hermitian. In other words, if the Hermitian conjugate of any operator is itself, so it is the same as the Hermitian conjugate operator, then we call this operator Hermitian. So what is the property of the Hermitian? The property of the Hermitian is that the expectation of the A operator is the same as the star of the expectation value of the A operator, where star refers to the complex conjugation, because this expectation value of the operator is a number. So both relations are identical and equivalent, so you could call them equivalent ways of saying that this A operator is a Hermitian operator. So, but the second relation is more meaningful in terms of the physical observable. So this expectation value of the operator is something that we can measure. Okay? So this tells us that when we take the measurements and take the expectation value of the A operator, this in general could be a complex value, right? In general, because the wave function itself could be a complex function, a function of complex variables. So, but if this A plays the same role as A dagger, or the expression value of the A operator is the same as the star of the same expression, and this tells us that this quantity is actually the real quantity. Okay, because A expression value is some, in general, complex number. It's the same as the star of that complex number, and you know very well, again, from your high school. So suppose expression value of A is actually A plus IB. It's a, in general, complex number, which is the same as A minus IB. Right? And A and B's are real numbers. So if A plus IB is the same as A minus IB, so what is the conclusion you get regarding B? B is what? What value? Tell me. Anyone know? Please raise your hand. If A plus IB is the same as A minus IB, and what is B? You tell me. Yes.
0.
Yes, 0. It's obvious, right? But it's not that trivial, right? Because if B is 0, you can simply just erase this B, right? Or imaginary part. Which means that this expression value of the A and A dagger, or A expression value star, is what? Is a real value. So this has a profound physical meaning. It means that this could be measured in your laboratory, because anything that you can measure in your laboratory should report to you a real value. Okay, so you cannot measure complex values observable, okay, because when we say it is physically observed, it is physical observable, which means that the expression value of that quantity should be real, which means that anything you could measure in the laboratory, the operators that corresponds to such a physical quantity should be Hermitian operator. So the simplest example of such a Hermitian operator is the Hamiltonian operator. Remember, the Hamiltonian operator, it is the kinetic energy operator plus the potential energy operator, right? So because the total energy, which you can measure in the laboratory, must be real. The energy is real, okay? And therefore, the operator that corresponds to the total energy of the quantum mechanical system, the H operator must be Hermitian. The energy is real, therefore H exponential value is actually the same as H exponential star. So H is Hermitian operator. Okay, so that's our call today. So we continue this Wednesday.